Welcome everyone to lesson 3.1 from Precalculus, which is all about periodic phenomena. So let's get started. Our big idea for this lesson, or one of the many big ideas for this lesson, is the idea of periodic or cyclic. So a relationship is periodic or cyclic if, and only if, the output values follow a repeating pattern as our inputs move forward. So you can think of things like the tides, you can think of things like moon phases, temperature, or even like light waves and sound waves use and follow periodic phenomena properties. So since we have a periodic relationship, we're talking about periodic relationships, anything that follows a repeating pattern, one cycle of the pattern from start to stop that repeats, the smallest one, is called the period. And analytically, what this means is that a period is the smallest positive k that we can add to our input to get the exact same output. And that always works. So it might be you have multiple places that give you 0, but it might do some weird things in between the zeros. So you just have to be careful that everything matches 1-to-1 by that horizontal transfer. So if we look here, it says given one period of the periodic function, sketch the rest of the graph. So what we're going to do is we're going to take the pattern we see and we're going to basically transplant it horizontally in both directions. So if I look here, it looks like the pattern is repeating every 8. Let me get a good marker for this. Because red's probably good for that. So it looks like it's repeating every 8. It starts at 0. And then goes up and hits a max at 2 after the 0, and then 2 after that it goes back down, so it's not quite going back down after this, so it's going to look a little bit like that. And then going backwards, we follow the same pattern, but we're going to do it in reverse, so So going backwards, we're going to follow the same pattern, but, backwards. So we start at 0 here, and then it goes down at 2 before the 0, hit 0 again, 2 before that, so on and so forth. So we're going down at -2 to a minimum of -3, back up at 4, and then that goes all the way back up at -6. So we're going to get this pattern here. So we're just translating that pattern, essentially, copy and pasting it forever and ever and ever. And not all periodic phenomena has to be nice, smooth curves, although most of them are, most of the ones we're going to talk about are. They could be like linear spikes, if you will, or absolute value-esque functions. We're just going to repeat that pattern. It goes 2, 0, 2, 1, 2. So 2, 0, 2, 1, 2. So one period to the right would look like this. It did not like that. Let's fix that. There we are. And then going backwards, we're going to follow the same pattern. We're just going to go backwards with it. So it goes 2, 1, 2, 0, 2. So 2, 1, 2, 0, 2. And if we connect those dots there, again, it doesn't like that for some reason. We get this nice periodic relation. It's not really nice, but we get this periodic relationship, and that's how we would sketch, and that's how periods work. So if a period is the shortest amount of time it takes for all of the values to repeat themselves, how can we identify the length of a period within a periodic function? So usually these functions are sine-esque curves, is what we're going to call it. Well, we'll get to them later. These smooth curves, we can map a max to a max or a min to a min is what I would recommend. So if I look here, I have a max at 1/4, I have a max at 3/4. So this distance would be the period. So I would do 3/4, take away 1/4, and that should give me 1/2 would be the period. Identifying the period, again, we can go from max to max or min to min. Sometimes you don't see a whole lot of the function, or the periods are very, very long and outstretched. So you have to work with what you got. So if I look at this function here, I really don't see 2 maxes. And you never want to go middle to middle because you don't, usually the function crosses the middle more than once throughout the period. So always stick with like a max value and a max value or something like that. or corresponding values. So I'm going to do minimum to minimum here, and I have 12 and -4, so we essentially have the larger number take away the smaller number, 12 minus -4, which is 16, would be the period of this function. So not too bad. Pretty easy stuff, really. Let's answer some questions about a function only being given one period. So this is where we can do something cool, and I'm going to try to introduce to you guys what's called modular arithmetic. But I don't want to stress you out now about it. I really want us to play with it in class. But essentially, we are given this nice curve. It starts at 2 at 0, and then at 1 it's 0, at 2 it's -2, at 3 it's 0, and 4 is 2. Let's figure out what's going on here first, and then we can try to answer some of the following questions based off of our observations. So if I look here on this interval, I know that it is decreasing, and it's decreasing from 0 to 2. So it's decreasing from 0 to 2. So it's increasing from 2 to 4. Concavity, I know that it's concave up from 1 to 3. So concave up from 1 to 3. And concave down would be from 0 to 1 or 3 to 4. So 0 to 1, 3 to 4. That's great. I can also see that it's hitting maxes at 0 and 4, and then it's hitting mins at 2. So what does this mean, like, for us? Well, it's repeating this pattern, right? And it's repeating this pattern every 4. The period here is very simply 4. So it's repeating this pattern every 4 increments, every 4 units. So if I'm looking at the function from 18 to 20, what does that mean in terms of us and repeating every 4? Well, multiplication is repeated addition. Division is repeated subtraction, right? So if I continue to subtract 4 from this, what do I get? Well, I can divide 18 by 4, and if I divide 18 by 4, that's 4.5. So I would have a remainder of 2 if I were to divide that from x. And then this is just 2 larger. So this is asking me exactly the same question of what's happening from 2 to 4. Well, from 2 to 4, the function increasing, decreasing, or both. From 2 to 4, it is increasing only. So that's nice. Concave up, concave down, 31 to 33. We can do this same kind of idea. 31 is 1 less than a multiple of 4, so that would make it a remainder of 3. And 33 is just 2 larger, so that's 5. So what's happening at 5? Well, it would be going back down. So we're looking from 3 to 5. Is it concave up or concave down or both? It looks to only be concave down there. So concave down. Finally, is a relative max, min, or neither at 82? 82. Well, 80 is a multiple of 4, so this is asking what's happening at 2. At 2, we have a minimum. So not too bad, but this idea of, well, it repeats every 4 really ties in this idea of modular arithmetic in the future. So I really want to talk about that during class, although if you get curious, by all means, go ahead and ask some questions, look some stuff up. But that'll be it for us. If you have any questions about periodic phenomena, please make sure that you ask them in class. Otherwise, I'll see you in the next lesson.